I now turn the floor over to Rachel.
Thanks. I'm happy to be up here welcoming Dr. Dan Kammen, who comes to us from UC Berkeley, where he is a professor of energy with the Energy and Resources Group, the Goldman School of Public Policy, and the Department of Nuclear Engineering. At UC Berkeley, Dan founded the Renewable and Appropriate Energy Laboratory and was director of Transportation Sustainability Research Center from 2007 to 2015. Dr. Kammen's research insights have had many broader impacts. He has been active in policy advising, currently serving as science envoy for the US State Department, and over the years advising California government, US EPA, DOE, US Aid, and OSTP. He has also founded several companies. We are excited to warmly welcome Dr. Kammen today to share his insights on the transition to sustainable energy.
Thanks so much. Well, my thanks to everyone for being here and to the Energy Institute for setting up this really interesting forum. I will try to both upscale the conversation to the energy systems on a little larger scale in ways that Klaus highlighted, but then also, as you'll see later on, kind of try to focus back down on this particular issue of negative carbon as part of the process. And so I'll do this at a sort of a high level. I'm a physicist by training, and so what we've done so far is kind of much more the bread and butter of what we often get into in our laboratory, but because of the title I was happily took on, and because of the changes going on globally, this will be much more of a policy level talk. And so I'm hoping that the interactions will be obvious as we go, and then we'll get back into some of them in the conversation. I do have this interesting role of a science envoy for the State Department, which does not account for the black eye. That's actually a basketball injury, not a Washington, D.C. injury. But that is going to be a bit of a theme here. And the question really is, how do we think about this decarbonization pathway that we need and the real challenges we've just seen in terms of different technology pathways and some of the terrestrial and ocean sequestration, some of the issues around BECCS, the biomass, and carbon negative energy. And again, I'll try to tie these together, but in a little larger framework. And for me, that framework is actually that despite what I would say is a interesting scientifically but very challenging economic and chemical engineering story for many of the details for how to get this significant amount of negative carbon we're going to need in the process, that the global community is progressing in a very interesting way. And the science and the analysis of how to do this is, I would say, in a remarkably good state, given how little we've actually invested in trying to make the global carbon sustainable energy story work. And I'm going to try to unpack that as we go. So to my mind, that says that the 2-degree by 2050 pathway is still alive. It might be on a bit of life support right now, but it is alive. And even the discussions about the 1.5-degree or less, the so-called high ambition strategies, these are things that we could technically do. And the challenge is going to be that everyone in the group, myself very much included, come at this initially from a science or technology pathway. And I'm going to argue, as my highest level point here, is that this is not where our challenge is. This is critically important. It's an absolutely necessary substrate. If we don't have enough science, engineering capacity, we don't get there. But that is not ultimately what our biggest problems are. And our biggest problems are that we're not understanding many of the political and societal aspects of how to do this. And so my lesson is really that we have the evolving science base to get there. We do not need to cut budgets. We need to increase budgets in research and development, but we need to think about this compact with utilities, with state governments, with industry, but with the petrochemical industry and others in a much more active way than we're doing now. And I won't get into it in a large amount of the story, but I think that this is really true on the so-called on-grid, the large utility scale technology we talk about here, but equally or even more critically in the off-grid completely underserved parts of the population around the planet for which demand is very high. And the lower estimate is that we have about 1.5 billion people off grid without basic energy services today. And if we do the accounting a little more broadly, people that are on grid, cities that are on grid, but the energy systems are not reliable or not cost effective, that number could be as high as 3 billion out of 7 billion people are under or unserved today. And figuring out how to meet that growing unmet demand with clean, sustainable energy has to be part of this equation we're talking about, even as we get into some of the details about carbon negative systems at the high tech level. So I won't do a huge run through just to motivate it, but I would say that we were on an incredibly negative pathway. I don't mean that in the way we're talking about today. I mean a bad pathway in terms of figuring out what would be some of the government-to-government, government-to-private sector alliances in this area, arguably until the US and China stepped out of the 25-year negotiation process and essentially had a two-country, a G2, if you will, of energy and emissions. Of course, the US and China, 40% of global energy demand, 40% of global emissions, essentially said we're going to hijack the climate negotiation process that goes back to the Kyoto Protocol and before, and just said we're going to have our own deal. And their own deal, very unconventional in a lot of ways. The US and China didn't have agreement domestically at home, as we now see. Didn't even agree to do the same thing by the same year. The US target year was 2025. The Chinese target year was 2030. What they agreed to do, or President Obama and Premier Xi agreed to do, wasn't even exactly the same thing. There's lots and lots of reasons that you can poke holes in that. But what came out of it was essentially a process that took that business as usual, that 4 to 5 degree pathway that the world was on, and enabled a conversation where countries submitted proposals to the Paris Climate Accord in 2015 that if the countries do what they said, which is a massive if, that's not a footnote, that is a high level if, that would essentially cut off this pink area of the growth curve, a wonderful strategy. And in fact, in the euphoria after Paris, not only was the Paris Accord ratified in record time, but there was a second negotiation around HCFCs that resulted in the Kigali Accord that essentially would cut off another ½ degree from this. So wonderful euphoria, but all about things we haven't done yet. But it very clearly leaves aside, it very clearly highlights that this is what countries promise to do, no clear way to vet them. And that leaves this gray triangle, sort of one of the wedges we heard about before, if you will, as a set of innovations not yet envisioned. So promises, innovations we need, that's a long, complicated story, and more or less it adds up to what we heard both in Sally and Klaus's talk before, and that is the pathway that we were on looks like we were doing this, and we are somewhere, if countries make good on what they promised, and that if is massive, somewhere in the middle here, but to meet the climate goals, we need to be down here in these greens and blues, and this begins to bring in a significant number of pathways or trajectories of innovation and deployment that get us into the carbon negative territory. And that's really why we're all here today. But to highlight that this process has an incredibly small amount of these deployment efforts in place. And we talked about Sleipner, we talked about other projects that are at best at the megaton per year level when gigatons are needed, is not just a let's scale these up. That's a re-envisioning of the problem, and Klaus highlighted in particular a couple aspects of that story. The good news, however, was that in my opinion, one of the most innovative policy frameworks that we had seen in the United States since the Clean Air Act essentially said each state should come up with its own target to meet what President Obama had recommended. And the Clean Power Plan called for each state to cut its emissions by about 1/3 by 2025 relative to their baseline. And so it wasn't competing the greenest states, the New Jerseys, Californias, New Yorks, Wisconsins, against those states with the highest carbon footprints at that time, but it was to compete each state against its own baseline. And so some places, a transition to clean natural gas, other places, a transition more to renewables. It was a battle against oneself. And I really thought that for a lot of reasons, this was near brilliant in how it was set up. And of course, now that the Clean Power Plan is officially on hold or worse, we are in a very odd situation. But it highlights, I think, the context in which these negative carbon processes need to be highlighted. And so I'm going to spend a little bit of my time highlighting a version of that story. And no surprise, I'll use California as a test case, not for what California's done relative to other states, but because it contains elements that I think allow an analysis on the science and on the cost-effective technical implementation of all the pathways we've heard to get looked at. And so a feature of the debate in California, and I would say the debate in Germany, the debate in Portugal, in Korea, Japan, Denmark, a number of places, Kenya, Bangladesh, a number of others, is that the climate energy story wasn't based around a specific individual and sometimes shaky decision. It was based on a much broader picture. And I want to highlight that with something which I think is one of the nice ways to think about it. And I'll explain what I mean by this shaky individual decision in a second. So if California, fifth largest economy on the planet, last time I checked, although it bumps up and down with every tax cycle, if this box represents California's projected business as usual emissions for 2050, then the story is that by 2050, we need to roughly cut that box down to this little box here, 80% or more reduction. And instead of thinking about each piece of legislation or each subsidy proposal individually, what California did was to say, overall, our strategy, if we think about this box of emissions as a mixture of electrifying our energy demands or liquid fuels, whether they're fossil fuels or biofuels, that's one axis. And the other axis is how greenhouse gas intensive our fuels are. And with that framework, the different strategies that often look very confusing scientifically, technically, and very confusing to the public and to legislatures becomes a little easier to put together. And so in the California story, the argument has been very strongly, we need to be massively efficient on every possible decision, on requirements for industry, on rebates to industry and consumers, and that constricts the box and pushes both sides in. So less energy overall has to be the basic part of the story. And from there, after a significant flirtation with biofuels, California decided, for a variety of reasons that I'll only highlight very briefly later on because I'm using up a lot of time in this sort of broader discussion, that we were going to massively push to electrify everything possible. And the dual benefits of that are that we are going to use clean electricity for everything possible, domestic use, industrial use, vehicles, commercial energy, industrial energy, and we're going to then push this whole remaining box as far towards electricity as we can. A whole series of other regulations on electricity, on liquid fuels, on industrial processes are used to always select the cleaner options on all cases. And that then leaves us at this box at the end. And the reason why I've sort of spent a lot of my time in the talk highlighting this story is because as the complexities of the technologies we've talked about in the first three sessions have highlighted, if you don't have an overall perspective on how this is going to come together, it makes the individual arguments over a given case very difficult. If you know and understand how they fit in, you get a different story. And so in the legislative battles in California, I would say in Korea, Japan, and Germany in particular, this kind of broader understanding of how a given investment fits in has really enabled a process where the battles became a battle over substance and not as much as a partisan divide over what you do. So one of the things that our lab at Berkeley has done in a number of countries is to build models of the electricity sector to understand the options and the costs for all of these technology systems. And so starting in California, we then have built very, very detailed models of the electricity sector Initially in California, which is part of something called the WEC, the Western Electricity Coordinating Council, that engages part of Canada, Western Mexico. We've now built models that are in use by the planning authorities and research colleagues at universities. Number of Western states. We will be releasing our version of this model, which is called Switch, for Mexico quite soon. We released a version for Nicaragua and Kenya and Chile as small economies. We have a very large team, actually ironically bigger than our team working on the North American version, working on the Chinese version. And we built the version for India. We got the data in a moment of, I would say, policy weakness. After the blackouts in India, we were asked to model it. But for a whole variety of interesting reasons, we have not released and probably will never release the Switch India model unless the government of India does it for us. All of those modeling packages look very similar. They are large linear programs where the cost of generation technology, the cost of transmission, the cost or benefits of energy efficiency are all included in a very large power systems planning model. And the types of innovations that really change how we think about these systems is to look at a technology path that was alluded to by a number of researchers, and that is the remarkable cost declines that we've seen for a couple technologies. Solar is the one that gets the lion's share of attention because of this remarkable cost decline, and for the non-scientist engineers in the room noted this is price, but in log units, not against time, but against total deployment. And this picture of a so-called learning curve, a roughly 20% cost decline for every doubling of the number of units deployed, is a piece of sort of debated and contested economics. We observe it in the real world in technology after technology. How it fits into kind of a basic canon of economic theory is a little bit of debate. But for technologies that you can mass produce and deploy, we see this from everything from energy systems to laptop computers to cell phones to condoms to anything that gets mass produced. We see this sort of effect. And it's a critical part of the story because the fact that we see it for so many technologies means that you can effectively forward price, or you can bank on it to deploy more of a technology through subsidies or policies or encouraging manufacturing, and if those technologies get in the field, really observe this dramatic decline. I will not go through the details of it, but to highlight, except for today, the cheapest large-scale power plant installed anywhere in the world in 2016 was not coal, not gas, not wind, not any of these things. It was solar deployed in the Middle East. Now, Middle East is a great solar resource, although it turns out their solar resource is not quite as good as you would think because they suffer from a dust problem far more severe than we deal with here. Often 30% reduction in output because of the problems of dust and some of the North African and Middle Eastern winds. But solar at under 3 cents per kilowatt hour has now been bid for, and construction is underway in 3 different locations. And you just can't talk, I mean, those numbers are just sort of off scale for where we're going. It's not a feature that means solar is going to be the single dominant technology, although we just had solar in California being 50% on a given day of total energy consumption, not of capacity, but of actual electricity. So it's a remarkable story. And the question is, how much does it apply elsewhere? And so without going into details, one story we are seeing today for all of the challenges of energy storage, the emerging technologies from chemical storage to compressed air to mechanical storage, flywheels, flow batteries, the same exact picture I just described for solar is actually one where the storage industry, for the amount of money deployed in it so far, which is nowhere near enough, is actually doing better than solar was in its early days. That 20% price decline that we've seen for solar, things are going faster than that in storage for an industry that we're deploying far less money in the picture overall. And so to try to tie these points together, I will not go through the wonderful details of this switch model, and switch stands for solar and wind integrated with transmission and conventional sources. It's proven we don't quite know how to spell totally, but it's a good acronym. starts to give us pictures of energy systems that take advantage of these technologies. And so here is a kind of a picture, a snapshot of a modeled day in the Western United States, very similar to the pictures we look at for China, Kenya, et cetera. And this is, the black line is the demand, and I've just stitched together 2 days out of the modeling run. 1 day is a peak demand day, the other is an average day. And the colors should be representative. Light blue is wind, yellow is solar, this orange is solar thermal, so I should say yellow is photovoltaics, solar thermal. We have gas with carbon capture, we've talked about before. Geothermal is red. There's a tiny band down here, which is actually nuclear, something we should talk about. And then these negative going spikes at the bottom is the amount of energy going into and then coming out of storage. And so what I'm going to sort of conclude on, in some sense, I'll do a couple slides to wrap it up, is the following story. This is a snapshot every 10 years of the evolution that we use to look at this, this sort of mix of energy. This is for Western North America. And while I don't hope you, I hope if you can see it, great, but we don't need to delve into the details, but each of these is a different scenario that we're looking at for this mix overall. Our reference case is the one on the left. There are cases where solar becomes even cheaper than it is today. There are cases where solar basically asymptotes and the price doesn't get much less. There are cases where we have low-cost solar, but also low-cost storage. There's cases where nuclear's costs are dramatically lower than they are today. There are cases where natural gas is leaking from the system. Cases where we constrain the use of hydro, not that we don't have the water, but we want to save it for nature and agriculture, et cetera. And I kind of present this sort of dizzying array of different cases to highlight that with technologies that we have today that we're quite certain about where they're going, all of these scenarios meet that 2-degree target. And let's throw out the one where we're not energy efficient for the arguments we've made before, but these all highlight that we have technology pathways to get us to this 2-degree number at quite reasonable cost. In fact, many of the lowest cost energy cases here are, so many of these cases are actually cheaper than we think the price would go to just based on our business as usual case because of the savings that we would get by investing in solar and wind and biomass and geothermal, et cetera. That doesn't get us to these biomass, to these negative carbon cases we're talking about. These are all on the generation side with clean energy or with an admixture of natural gas or bits of coal. They don't get us to the cases that you've heard in the 3 previous speakers. And so the need to do significant R&D in all the cases we've heard about before, onshore, offshore, biomass-based and others, is a critical part of the story. But this, we'd like to think, gives you hope. And what I want to conclude with is that each of these scenarios are ones that we've built in conjunction with the utilities that we work with in the regions. And so in China, in East Africa, South America, and this is just highlighting the Western North America one, all of these say we have paths to get us close, but this critical negative push that we would need to make those 2050 pathways happen is the piece that we're not researching anywhere near enough in this story. So this mixture of understanding and planning these pathways, but understanding how this negative piece would come into the story is a kind of big missing element of the story. And I guess the take-home message to conclude at the end is that while all these pathways, you'll have advocates for them on the science or engineering side, the choices that need to be made here are not trivial. And by that I mean, let's say that we invest strongly in these very distributed solar and wind and storage pathways. That requires an investment in the transmission system, the distribution system, and energy efficiency that if we don't do, the costs are much higher. If, for example, nuclear were to play a much larger role, not something that we're seeing in California, but you can make an argument for it, you would invest very differently in the transmission infrastructure that you need because you basically don't need to build much more. The solar renewable ones require a very different investment. that gets me to my to the last point, and that was that we find these are inherently not technology-limited decisions at the end of the game. They are, do we work with industry? Do we find ways to make these pathways appealing to utilities as they exist today or as they might be in the future? And so that really takes, I hope, the argument about what mixture of clean energy systems, carbon negative systems do we want to invest in out of just the science and engineering conversation to a much larger policy, human engagement one, whether it's in small energy systems like Kenya or large ones like China and the Western United States. So thank you all for letting me kind of frame it in a bit of a larger way, and I look forward to the conversation.
We have time for a couple of questions.
Thank you for this. The question I have is, customers, at least in our country, are very specific that they want to be self-reliant, especially when you have, say, ideas, extreme weather, possible tourism events taking down substations, transmission lines, whatever it is. Clearly, distributed energy resources is the way to go. Typically, utilities don't want to go that way. And I'm really into the solar, offshore wind, and storage. How do you see that going economically compared to some of these other things? It makes sense to me, but again, you're fighting the power of utilities for the most part.
Yeah, so, boy, great question. I mean, there's sort of a broad philosophical answer, which I think is important, but is sort of not that useful in the day-to-day. How do you make it happen? And then there's the more detailed one, i.e., how do you interact with the public utility commissions state by state? How do you make this story attractive to utilities? And so, as an example, in California, the program to really grow the solar industry has some very clear pluses and some critical reliance on the larger global story. That learning curve graph that I highlighted here for solar is one that each of these dots, whoops, I had the same problem that you did with too aggressive use of the pointer. Each of these were significant scientific or engineering innovations that contributed to enabling this remarkable cost decline for solar. But ultimately, it was large-scale manufacturing, not exclusively, but largely in China, that allowed the deployment part of that story. So Germany, I would say Japan first, and then Germany, then California, and now many others, contributed by making their markets friendly to solar, either by subsidizing or by having utility-scale mandates. In California, ironically, we are ahead of schedule to meet our 2020 climate target, and we are on schedule to meet our 2030 climate target, and it's essentially one that has taken advantage of this low-cost solar. The utilities today in California get credit for large utility-scale solar. And just recently I mentioned that we had about 9 gigawatts peak. We had about 9 out of 30 gigawatt peak energy coming from utility scale solar and about another 5 coming from distributed rooftop solar. The utilities get credit for that large scale desert-based solar generally. They get no credit. In fact, they get a whole bunch of negatives and costs put in their way to do the distributed household solar. Anyone thinking about sustainability, think this is crazy. Why can't you give them credit for the rooftop solar that I have and actually about 600,000 other Californians have? So the enabling part of this conversation is how do you incentivize the utilities by changing the rules of the game so they get credit for all that rooftop solar or for installing storage in the basement of buildings or for investing in pilot scale carbon capture plants. That part of the story is largely broken. A few utilities do it, but very, very few. So apologies for doing it kind of a high level, but it's a great point.
So Dan, there's a very big concern among a lot of utility companies about the so-called death spiral. So you put in more and more solar, and they still have to be the backup in supplying the electricity.
Correct.
And and that's actually happening in Germany. So how do we avoid this in the present business models of public utilities?
So something which I didn't highlight in here, but which we all sort of assume, oh, sorry, I meant, I was jumping to that one slide. I was thinking, yeah, if you can. Which slide do you want? It's this one right here. That one? Yep. So when we talk about large-scale energy systems, we either think utility-scale large projects or distributed down at the level of solar on my rooftop or another individual technology. We have done almost nothing to explore the middle ground. We haven't done anything on the technical, or very little, on the technical and economic level to say what actually is the right scale to make economically viable decarbonization units. And so an example of the sort of projects that we're just starting to see, this is one that we're doing with colleagues at Lawrence Berkeley National Labs, Stanford, NASA, and others. There's a similar effort in Cincinnati. There's another effort in Cambridge, Massachusetts, that are wondering, is it the household, is it the industrial building, is it the block scale that allows you to capture the economies of the different technologies? And so here is one project. It's 40 homes in a very low income area of Oakland, California, which are wiring themselves as a mini grid, but not a mini grid in a very rural location. This is a mini grid right downtown, where they are sharing the rooftop space to install solar. They have invested in one vacant lot becoming a centralized storage location using flywheels in this case, actually, to store energy, and at the same time to then replumb the neighborhood so they capture gray water. They use their excess energy for local purification. And so what we have found in a number of places, and these are happening in Japan and they're happening in the Netherlands, that there are intermediate scales that may actually be much more attractive to bring these systems online. The mixture of very distributed solar on my rooftop, which is sort of the death spiral you've described, versus these block scale systems is one example of trying to figure out what is both the scientific and what is the business model that allows utilities, which I say in a lowercase u, to persist in the future. And by that I mean the following. If the death spiral is that the best economic choice for everyone in this room is to have their home or their business entirely energy self-sufficient, that's a death spiral for traditional utilities. What's their purpose in such a system? There are some strong advocates for that, but most people analyzing these kinds of power systems like the switch model I described think that the economics looks much better for a system where utilities are rewarded for essentially being the eBay of energy, that each unit can buy and sell, but that utilities are both providing backup power and being paid for it and are connecting systems together. And so it's a long answer to the question, but it's essentially we haven't done enough of this sort of research across scales to figure out which are the business models that enable this decarbonization pathway that makes sense for current utilities or for evolved utilities, meaning utilities quite different than we have them today, or is this ultimately a race to totally decentralized systems, which I don't think that's going to be the winner, but there are some advocates for it. So I hope that pulled together what you asked. The panel? Thank you very much. Thank you.